So good afternoon, everybody. Welcome back to today's QuantTap seminar. So today I have the pleasure
good afternoon, everybody. Welcome back
to introduce
today's QuantTap seminar.
Introduce you Professor Christine Muschik from University of Waterloo. So Christine has got her PhD at Max Planck Institute for Quantum Optics in Munich, and then she had some very successful postdocs at ICFO in Barcelona and at IQOCI in Innsbruck, visiting and experiencing the great atmosphere of some of nicest and more active institutions in Europe in quantum information and quantum science. And today, Christine will present us some of her recent work on simulation of lattice gauge theory on quantum computers, also beyond one-dimensional system. So, Christine, welcome. The floor is yours, please.
Thank you. Yeah, so thanks a lot for inviting me to your seminar series and also for this very nice introduction. I hope you can see my slide now. Yes, okay, perfect. So as you already said, the overarching theme of my talk is gauge theories for high energy physics on a quantum computer, and very specifically also the two questions, how to go towards 2D and how to go towards non-abelian series. And yeah, these are the questions that we are looking at here in Waterloo, so at the Institute for Quantum Computing and also at the Perimeter Institute. Yeah, except that right now we cannot be there. We have a stay-at-home order, so this is our team interacting on Zoom because we're all working from home. But we hope that we can go back to our institute back soon. And yeah, we do have a postdoc position available. So if you're interested in joining us, so yeah, please shoot me an email. So back to today's talk. It's about using the emerging quantum technology, quantum computers, to learn about fundamental particle interactions by developing quantum simulations of gauge theories specifically. And yeah, I'm sure that everybody in this particular audience is very aware how gauge theories are so fundamental for so many areas in physics, and in particular condensed matter physics and high energy physics. And for the talk today, I'm going to talk about gauge theories for high energy physics. And there are just many open questions in modern science which really necessitate new simulation methods for gauge theories. And here is one slide with the big dream, so to say, because this slide basically summarizes really unsurmountable big challenges in modern science, which are completely inaccessible to the current Markov-Chain Monte Carlo methods because they're sign problem afflicted. So I'm just here mentioning dynamics, yeah, real-time evolutions, yeah. So questions on, yeah, heavy ion collisions and particle colliders, or deep question how the universe evolved at its earliest moments, or topology, yeah. So why is there more matter than antimatter in the universe, yeah? So the standard model does not predict that. I mean, not by a far shot. And if a theory cracks and fails in such a big way, it might be a hint for new physics. And except that some models for studying this, like so-called topological models, cannot be studied because there are topological terms which lead to a sign problem. And again, Markov-Chain Monte Carlo is out of the window. Or, yeah, problems of finite fermionic chemical potential, extreme density, like, for instance, what happens inside a neutron star. Like, these are all questions where we see a possibility to break through the current computational roadblock by building quantum computers. That's just a scientific opportunity to explore here. And I'd like to mention that there's, of course, an alternative path. Like one very promising alternative path is to run tensor network state calculations on classical computers, especially since our chairman today, like he's really pushing the forefront, like really pushing what is possible with this approach. But for my talk today, I will really talk about quantum simulations, even so both paths are really actively pursued on this quest to find non-sign problem afflicted methods. This is exactly the point in time when a disclaimer slide is in order, yeah, because now I brought up all these big motivating things, these big questions that we want to learn new physics, but that's going to happen in the future. And like we're here in 2021, so on the very left of this time axis, and yeah, we really need to learn how to walk before we can learn how to run. So we are really in the early development stage. Yeah, we want to develop a new type of quantum simulator, one that is suitable for gauge theories, for high energy physics. And there are so many concepts that still need to be found out, developed, and found. Yeah, and so we are really aiming at proof of concept demonstrations of these new concepts. So we are not yet competing with the classical methods today. Yeah, so having said that, with this disclaimer in mind, we are a young field, yeah, but I'm very happy to say, despite the fact that we are young, we have seen some very exciting proof of concept demonstrations already, like in the lab. So this is happening like experimentally, and I'm listing them here. There are more, obviously, and there's a very nice Qt flag review article that you can look at if you're interested into more details specifically in the progress of this field. And from now, I'm giving you bird's eye view, but through my personal lens. Yeah, so if I look at the proof of concept demonstrations that we saw in the lab today, then of course everything is low dimensional benchmarking models for developing the concepts. And I'm grouping them here in abelian and non-abelian, where non-abelian is very close to my heart, because only if we have color degrees of freedom, only if we have non-abelian theory, this really allows for having baryons, like protons, neutrons. And by baryon, I mean really gauge singlets, like gauge invariant states, neutral states with non-zero matter-antimatter imbalance, where you have really matter coming together in composite objects without the equal amount of antimatter. Okay, so, and long story short, so for abelian, yeah, we can do 1D with matter, has been demonstrated in the lab. In 2D, there were also demonstrations, well, not with dynamical matter, but at least pure gauge theory has been shown. And for non-abelian, it's an exciting time for non-abelian, yeah? Both in terms of tensor network states, but also exciting time right now, this year, last year, for quantum simulation, because there have been first demonstrations for 1D and 2D, no dynamical matter so far, but I'm very proud and happy actually that we can add a tick mark here. So I'm going to talk about this towards the end of my talk, how we succeeded in doing a non-abelian gauge theory complete with the dynamical matter, and like really with the perspective to see baryons and as a starting point for all of this. Okay, so, but this is my personal journey, and in red is a part of my journey that I'd like to share today. So I'm not going to talk about the first two, which is 1D QED from 2016 and 19. I will focus really on the brand new things, from 2021. And this is how we pushed and generalized these methods for 1D to go towards 2D QED. So we're going 2D in the abelian case. And in an independent effort, we also studied very hard how to go non-abelian. But since non-abelian is so much harder, we did this in 1D. Of course, the big thing for the future is that I want to put both together, right? So ultimately, I want to be beyond 1D and I want to be non-abelian. But for now, at least my team, we approach both individually. Yeah, like these two legs on which we can now stand. Okay, and with this, this talk will basically be mostly going towards 2D and abelian, because the concepts are easier to explain if you don't have the colors around. And yeah, then in the end of my talk, which will be considerably shorter, I will explain how we did a non-abelian simulation and showed the variance. Okay, so we can start with going towards 2D. That's actually here the executive summary. Everything else is just detail. So as I just convinced you, or if you're an audience of this lecture series, you will be convinced already that there are important open questions in gauge theory that cannot be tackled with current methods, and that quantum simulators offer the path forward. But simulating gauge theories with matter beyond 1D, that's really challenging, at least if you want to do it in the lab and not only on paper. And therefore, we developed quantum simulation tools for studying 2D physics in gauge theories today. So by today, I mean with really current devices. And my slide does not move. Oh, no, it does. Okay. Right, and I want to just point out that there's really a big jump if you go from 1D to 2D and 3D, because only beyond the 1D we have magnetic field effects, non-trivial ones, and only then Fermi statistics really play a role. And now my slide does again not move. No, it does. Okay. So as I was just about to say, we have much more physics in 2D and 3D, but we have also much more challenges, if we want to bring it to life in the lab. And so I'm going to talk a bit about our proposal, which is a proposal for trapped ions that allows you to observe running coupling and dynamically generated magnetic fields in a present-day trapped ion quantum computer. And these are both effects that are completely absent in 1D. So these are just 2D phenomena that you can start studying. And the whole thing really consists of 2 steps. The first step is encoding, encoded in an effective spin model, in a qubit model, just something that can run on a quantum computer. But once we have encoded our theory in an effective qubit model, then it's a whole challenge. Okay, now how to implement it on your quantum device? It's a whole different question. And so I address both of them separately. But before I do, let me mention our guiding themes. We had 2 guiding themes. The first one is to allow for proof of concept demonstrations in the lab today, like not in 20 years from now, but like really with the NISQ devices that we have now. And we made that possible by introducing a resource-efficient encoding, introducing a new truncation scheme for the gauge fields, and then an efficient Bqe framework. And as I will explain today, putting all 3 together in a nice, neat package allows you to do it today. And also we wanted to have a perspective for the big future. So the perspective is to reach the continuum limit, because of course our physics question is in the continuum theory. Then one discretizes space and runs it on a simulator with finite resources, and then you get an answer. What does this answer tell you? Is it like overwhelmed by finite size effects, or is there a perspective to do the continuum limit and really answer your physics question? So this is like key for making a meaningful simulation. And of course, our simulators now are small, but I want a scheme that is in principle able, if our quantum computers grow, to go there and answer questions in a meaningful way. And unfortunately, I don't have the time to talk about it today, but we took care of that through a Hilbert space truncation, which all the details are in this paper, and unfortunately I'm not going into any details today. I'm just telling you this proposal has this perspective. And that was something that I consider indeed important for the field to move forward, that we think about these questions. Okay, so now I can dive right into the first step, encoding of the gauge theory in an effective spin model. I'm explaining it for the abelian case, but expect it to be done in the non-abelian case very similarly. Okay, so here's lattice QED with matter fields on the vertices and the gauge fields on the links. And I'm zooming in to one building block. So this is one individual plaquette out of our big lattice. And on each of the links, we have private individual gauge fields, so electric fields and vector potentials in this case. And now I'm zooming in on one link on this individual plaquette, and one link is now this gauge field, which I'm depicting in the electric field eigenbasis. Yeah, and so it's like really an infinite dimension system. So it's an infinite discrete spectrum. 0 is the vacuum, and then we have 1, 2, 3, 4 fluxes up to infinity, or -1, -2. That would be units of fluxes of electric field, but in the other direction. So infinite in both direction. And we have the Gauss law. So if we just mentally go back to 3 dimensions, so to the continuum, just for a minute, yeah, then in classical quantum electrodynamics, we know that the divergence of the electric field is a charge density. Yeah, so the charges are the sources of the electric field. And we can write this down in 2D, now go mentally to 2D, but also to discrete space. And so you see here, this is the divergence of the electric field just in 2D and in discretized space. And here we have our charge density, which is now an operator, can be 0 for the vacuum or ±1, depending whether you have an electron or positron directly on this link. So these define our local symmetry generators, and like really states obeying the Gauss law are really eigenstates of these local symmetry generators. So for this talk, let's say no external charges. So we're looking for eigenstates with eigenvalue 0. And if you assume that here in the middle, let's say we have vacuum on this particular lattice site, it means that the electric fields that come in have to equal the electric fields that come out. That's the intuition. And here's an example of a gauge invariant configuration, a configuration that obeys the Gauss law. So I like to call it a physical configuration also. So this state would obey the Gauss law. So we see here 2 positrons and 2 electrons. I have 0 fields outside here, and I have an electric flux +1 flowing here and electric flux -1 flowing here. It's a good combination. And by contrast, this configuration would not respect the Gauss law, right? So I have here 10 fluxes of electric field to the right, and there's just no way a single proton with charge 1 could be the source of 10 units of flux. Yeah? And another way to depict that is that this is a Hilbert space of all gauge degree of freedom and all dynamical matter degrees of freedom. It's very large. And this is a small blue blob of the experimentally so this is the exponentially small gauge invariant subspace. So this is exactly where all the physical states live. And like this candidate here with the unphysical +10, it would live outside. Yeah? So there are just many more. And many proposals just introduce a whole Hilbert space, yeah, and then one constrains the simulation to the small blue blob, and that's not what we're doing here. We are simulating only the small, exponentially small gauge invariant region here, and we do that by eliminating redundant gauge degrees of freedom. And yeah, this is just giving you the intuition for that. In 1D with open boundary conditions, you can absolutely eliminate all the gauge fields. Yeah, and that's because, yeah, if I specify open boundary condition with a certain background field here, then I have n-1 links, n-1 gauge fields in the middle, but if you do the math, you find none of them is independent. Can get rid of all of them, and it has been done. People do that. Yeah. If you go beyond 1D is what I like to do. Yeah, going beyond 1D, then we cannot eliminate all of them. Yeah, so just an example to look at, I have here a plaquette with open boundary conditions. In principle, I have these 4 gauge fields. We have 4 links, 4 gauge fields in our theory, but if you do the math and look how many constraints by the Gauss law you have, you find you can eliminate 3, and there's only 1 independent gauge degree of freedom. The rest is totally redundant. Yeah. And looking at this problem, it totally makes sense, no? Because we want 1 free gauge degree of freedom because it represents the magnetic flux that pierces the plaquette. So we expect that there's something left, and it should be that way. And yeah, that's a good thing. And yeah, we actually, if you want to look at our publication, we wrote down like everything, how you can put it on a quantum simulator for an open ladder system, for a full 2D periodic plane, and also with a nice, effective, intuitive description in terms of gauge invariant operators. Yeah, so it's very good to work with. And yeah, also you can do it also in 3D. So for instance, if you start with, as we did in this publication, start with 24 gauge fields in general, then you have only 14 independent ones for a periodic cube. Yeah? And so why do we do that? Because it just allows us to use much fewer qubits. I mean, there are other benefits also, but the main reason is we get rid of all the redundant gauge degree of freedom. And if we only simulate the ones that we actually need, obviously we use much fewer qubits. Okay. So there's a second thing that goes into encoding our theory in an effective qubit model, and that's this new truncation scheme for gauge fields. So I will only give the flavor here because I don't have time, but the executive summary is that, as you have seen, gauge fields, they live, of course, in an infinite dimensional Hilbert space. And we need to truncate them if we want to run them on finite dimensional hardware. But so we were first starting out using the existing normal schemes. And then we found out, oh my God, this leads really to an explosion of resources. Yeah, was not feasible. So therefore we developed a new truncation scheme that allows for minimal errors, but with modest resources. Yeah, so this is again the electric field eigenbasis, and well, we have to truncate somewhere. Yeah, but the question is where? Yeah, so these are, you would truncate differently for qubit system or bosonic systems. Yeah, we did different things for different systems, but the underlying mechanism is always you cut off some of the states. And then the question is, which description is sufficient? Can I get away with 2 levels? I mean, in most cases, the answer is no. Can I get away with 3 levels? Do I need 5 levels? Like, how do I know how much I need? And in particular, what one finds pretty soon is if I go closer to the continuum limit, then I find if I want to capture, for instance, the ground state property, I need more and more and more and more of these electric field eigenenergy levels. Yeah? And this is exactly where we saw this tremendous use of resources when we wanted to simulate regimes where the magnetic field effects dominate, and also since we wanted to see running coupling. Yeah, and this is basically where I want to make this advertisement for this paper here, which includes a resource-efficient protocol to simulate lattice gauge series with continuous gauge groups, SU1. Yeah? For instance, in the Hamiltonian formulation, it tells you like how to cut them, how to go on a magnetic basis, and yeah, we introduced something we call double scaling, and like for us, it really made the difference between feasible and non-feasible. Yeah. Okay, but that was just why we did it, not how we did it. That would be an entire talk on its own. Now I want to brutally switch gears and completely switch over, because now I just told you how we encode our model. Now I want to tell you how we implement it. Yeah? Because our target model, once we encode it, it includes exotic long-range interactions, as I will show you in a minute. It crucially involves 3 and 4 body terms, whereas our hardware, by contrast, does not support these interactions natively. Yeah, it only supports a restricted set of 1 and 2 body interactions. And this is why we introduced the Bqe that really avoids implementing these complicated target interactions on the quantum hardware. So to say it a bit more specifically, our target Hamiltonian, it contains 3 body terms because I want to go beyond 1D. And if you're beyond 1D, then the gauge invariant kinetic terms, they will be 3 body. Yeah? If I want to see magnetic field effects, they will be 4 body, my plaquette interactions. Yeah, and that's just inherent to the physics that I want to do. However, we also made our own lives even more hard. Yeah, because we introduced further complications. So as I just told you, we eliminated the gauge fields, and I only told you, oh great, we use fewer qubits, but we also pay a price, and it results in long-range interactions. Yeah. Also, it was our choice to use a fermionic model, but wanting to simulate it on a qubit computer. Could argue that's maybe our own choice, and it means we have to do a Jordan-Wigner transformation or something similar. And this also creates an overhead in the complexity of the model. Yeah? And last but not least, we have these gauge fields, and we also insist on encoding them into qubits, at least in this protocol. Well, and that again complicates our life. Yeah, so you see there are intrinsic complications, there are complications due to our approach, and gives rise to a very complicated model, which, long story short, is just a tremendous mismatch between our target Hamiltonian and our resource Hamiltonian. Yeah. And now we have several choices how to go about it. So you could go about it in trying to go to analog simulation, which I also did, which is a valid approach. But here I'm talking about a complementary approach, which is variational simulation, in which the target Hamiltonian, which has this 2, 3, and 4 body terms, and even above in our case, is never actually realized on the quantum hardware. So basically, you can see the Bqe as a bridge. Yeah, so it bridges our ugly target Hamiltonian with our available resource Hamiltonian. And I think a lot of our viewers are familiar with Bqe and hybrid approaches, but maybe not all. So I'm very quickly and briefly reviewing the underlying mechanism of what a variational quantum simulation really is. So it's basically a classical computer working with a quantum computer in tandem together in a closed feedback loop. So on the left, we have our classical computer, which runs optimization algorithms. This optimization algorithm has to evaluate a cost function. And the classical computer relegates this cost function evaluation to a quantum coprocessor, if you like. The only job of the quantum coprocessor is just to evaluate this cost function and report back the value to the classical computer. And then you have a closed optimization feedback loop. In more details, we specify the target Hamiltonian, and only the classical computer knows that. We specify what are our available resource Hamiltonians, and this depends on which platform you use. Yeah. So for instance, for the hadron experiment that I talk about later, we did it on the IBM computers. We had a universal gate set. Yeah. So for the 2D proposal that we have, we want to do it in a quantum computer made of ions. So we have the Hamiltonians that correspond to the trapped ions. If you would think about doing it on cold atoms, it would be some different Hamiltonian entirely. But basically, the aim of the game is that you create a variational ansatz state. You start here with an initial state which you can prepare easily, and then you apply a sequence of quenches or time evolution. So this Hamiltonian alternates here with the second in my example, but you don't have to alternate it. You make just the best possible ansatz for your problem. The important point is that these time evolutions, these gate applications, they have to have variational parameters here. So in our case, these classical variational parameters are the coupling strength or how long you apply it, but it doesn't have to be that. That's just in our case. And these classical variational parameters are exactly what the classical variational algorithm uses to vary the state in such a way that, for instance, if you're looking for the ground state, the energy is minimized. And by minimizing the energy, so this variational ansatz becomes approximation to the ground state. And so this was very general. And now I want to apply it for our proposal. So in our proposal, we think about a basic building block. Yeah. So if I want to make a 2D lattice, I first think about how to make a single plaquette. And here is the single plaquette with periodic boundary conditions. You can think of it as a torus, if you like, or you can depict a single periodic plaquette like this, whichever you like better. And what we propose in our proposal is to prepare the ground state. Yeah. And once you have the ground state, you can measure the plaquette expectation value, so in a sense, magnetic field energy, versus different values of the gauge matter coupling, the gauge coupling. And once you have that, you can, as we outline in our publication, you can see magnetic field effects, you can see the running coupling. And so here I'm showing our prediction for 3-level description, 5-level description. This is for a pure gauge theory here. And I'm skipping a lot of technical details because this would be probably a 2-hour lecture in itself. But we adjust this to see running coupling really in a trapped ion quantum computer with all the nuts and bolts and technical details that you need really for this particular platforms. And it's in a sense platform specific in the sense that it's specific to the available gate interactions in trapped ions, like local rotations and Möller-Sørensen interactions with arbitrary connectivity, but it's also problem specific. Yeah, so you were thinking probably that it's platform specific already, but it's this Bqe circuit design in order to make it efficient for current day hardware. It's also problem specific. Yeah? And again, I don't have time to go into detail, but this is a circuit. So I'm just showing it. So you see it's not terribly complex. It's a circuit adapted to the problem Hamiltonian. So this circuit basically corresponds to the torus. And I'm just mentioning that it's done in a way that it does not require prior knowledge of the ground state. So you only have to know the Hamiltonian. Yeah. It can be found efficiently. Yeah. And it can be generalized to larger lattices with a polynomial overhead, and it allows for efficient variational search. We simulated everything, like simulated how the trapped ion experiment would look like with 9 ions. And I'm going right to the outlook here with an outlook on extensions that you could make on this proposal to go then, so that everything was for one plaquette, but you could go to multiple plaquettes. It would be exciting to encode it in qubits instead of qubits for the gauge fields, will be way more efficient. And it will be also very interesting to try use this resource efficient encoding strategy for time evolutions. Also to generalize it to non-abelian series, hopefully. And then my personal dream to include finite fermionic chemical potentials in topological terms to really go to sign problem afflicted settings. And with this, I make a very radical jump now, because I also want to talk about the non-abelian simulation, which is brand new, which we just uploaded on the arXiv, basically. And with this, I want to specifically thank the team that I did that with. So here you see Randy Lewis. So we were really very, very happy that we had a particle physicist working with us on this, like he's at York University, very close up here in Toronto. And so the rest is like our IQC team. So our 2 first authors, Jinglai Zhang and Yasa Atas. And then also Jan Hase, who was really taking the lead on the Bqe part of this. And we also had a classical person in our team, yeah, just a classical optimizing postdoc. So just to set the stage and maybe also manage expectation a bit, that just a reminder that simulations of non-abelian gauge theories is something that happens only now. Yeah, it's very young. So I recommend these 3 publications in particular, so from Natalie and Martin and also Randy on doing a pure gauge theory of non-abelian models in the lab. And in this talk, I want to go one step beyond that by really including dynamical matter in the game. And I'm going to leave out a lot of details, but you can find them in our preprint. And so this is only talking about things that have been done really experimentally, but of course there is a plethora of interesting theory papers on how to go about this quest, like how to teach a quantum simulator really to implement also color degrees of freedom. In a nutshell, we simulated a non-abelian gauge theory with dynamically coupled matter on a quantum computer. So that was the goal. What does quantum computer mean? Quantum computer in this case meant the IBM quantum experience. Yeah, so it's superconducting qubits and it was accessed online. Yeah? And the approach we used was again the variational quantum classical approach. This is variational quantum eigensolver. And I really do believe that the variational quantum eigensolver approach is very powerful here because it allows us to write down a crazy complicated model and still simulate it. Yeah. And what we did actually is we prepared the ground state and the first excited state of the model in different baryon number sectors. And then we used that to compute the masses of the lowest meson and baryon states. So that's in a nutshell everything. So let me explain a bit more. But before I explain more, also let me outline the path. So as you can see here, the aim of the game is really, from my perspective, to teach a quantum computer, especially the quantum computers that we have now, how to simulate color degrees of freedom. And then I'd like to extend it to more complex models. And in particular, it will be key to extend this to higher dimensions. That's an important goal. And then adding topological terms and chemical potentials. And there's no fundamental roadblock inside. And then up in the future, hopefully we can learn new physics. And I was showing this here as a nice linear route. And this is, of course, a completely inadequate model. A much more realistic model would be this. Yeah, I think the field will be more like, the development of the field will be more like a jungle gym. Yeah, so there are several exciting goals, maybe one goal on the head of the dinosaur, maybe one goal where the root is, and you see you have several paths now. And we as a field, as a community, we have to figure out whether we go maybe here or there, and lots of ways to go. So I think it's not going to be a linear, straight process for us. Okay, so having been honest on that, let me zoom into the models that we looked at. So, of course, the big ultimate goal would be SU3, like in QCD, now in 3D. But for now, we do 2 colors. Like the goal is to learn how to include colors at all. Yeah, SU2. And we start in one spatial dimension with open boundary conditions, actually. So here's our lattice Hamiltonian. We're using the Kugo-Susskind formulation. I can tell you why this is our choice later. But for the moment, just run with me. So we have here a mass term, which gives us the rest mass, the kinetic energy term, the color electric field energy. Just a reminder for the mass term, the Kugo-Susskind formulation, we're using staggered fermions. So like really, we have this 2 component spinor with fermions and antifermions. I mean, both of them can be red or green with 2 colors in our case, but it's staggered in the sense that antifermions live only on the odd sides, and on the even sides we have the fermions. Yeah? So if I'm writing down a lattice of n lattice sides, so that's only n half original lattice points because of the staggerization. Yeah, and I think many people are, especially people who work on that, are very familiar, probably also with the invariant Casimir operator, the color electric field. And we also have a version of the Gauss law, as I discussed before. Only now our Gauss law, of course, is much more complicated because we have, again, the local gauge transformation generators as before. But now we have left and right fields, and we have color charges, yeah, with 3 different with 3 different generators here. So which makes everything much more complicated, but still one can play the same game. Yeah, so there has been a lot of work on how to play this game of reducing, like eliminating all the gauge degrees of freedom, especially also in the work by Ignatius Chirac and Iris Soha, which is something that we're heavily using here. But the aim of the game is really the same thing, not live in this big Hilbert space, but eliminate actually all color electric field degrees of freedom and come up with a pure matter model, which has only matter, no gauge fields, and is automatically gauge invariant. So that's basically the first box here. Going from our original model to an exotic spin Hamiltonian, that's encoding. But once we have encoded our model, we also need to vary. Okay, now we have this crazy complicated effective model. How on earth do we implemented on current day devices. So how can we see our baryon on a quantum computer? So I said this already in the beginning of the talk, why I'm especially keen to see the baryon. And that's something which is really different between abelian and non-abelian, because I really wanted to see something in this non-abelian model that we could not have observed so far. That was just out of the question in the abelian models that we have on quantum simulators so far. And this is just a reminder here. So if we have an abelian gauge theory, quantum electrodynamics, and you want to have a color singlet, I mean a gauge invariant configuration, composite gauge invariant configuration, then you have to combine as much matter as antimatter. So here's a meson, and you can only be neutral if you combine an electron with a positron. However, if we include color degrees of freedom, we're giving ourselves more freedom. So we have color, and therefore you have now two options. You have the old option, the meson option, which has zero matter-antimatter imbalance as before, that survives, but you get an entirely new option. And this new option, which lives only in non-abelian theories, is that you have really here a completely neutral, color-neutral gauge singlet, which is purely matter. So this is our baryon where the red and the green conspire together to give color-neutral color. Okay, and we did this whole encoding game of our Hamiltonian in the Kogut-Susskind formulation. So this is basically our Hamiltonian, and this is how our encoded version works. Encoded, reminder, means eliminating the gauge degree of freedom and mapping to qubits. To run it on our quantum computer, and you see it's fairly complicated now, as we have 4 body terms. You see all-to-all connectivity. I think it's safe to say that this qualifies as a complex model. And this is what we want to implement now, like really bring this on the IBM quantum machine. And as it turns out, as it's written there, it was indeed a bit too complex. It was actually too much, so we had to invent something on top of the regular Bqe. And so something on top is what we call Bqe Circuit Splitting. I don't have time to explain it here. I'm just telling you that we use that. Basically, it means if you have your ansatz, you can rearrange your terms such that you have everything which is not variational in the end. And basically, you can transfer it to your Hamiltonian, and you can transfer it to the classical post-processing. So basically what it does, it alleviates the requirements on your quantum coprocessor by relegating part of the computation to the classical computer. But still only in an effective way. And by this, one can reduce the number of qubits and the number of gates needed. And in our case, it was just desperately needed to reduce both the number of qubits and especially the number of gates. And then here are the results. As I said, we looked at the lightest baryon state and the lightest meson state. So to look here at the energy diagram, I'm separating the baryon number 0 to the left and the baryon number 1 to the right. So baryon number 0 is like really whenever I have as much matter as antimatter. So ground state in this sector is a vacuum, and the first excited state will be then our meson. And in the baryon number 1 subsector, the baryon is directly the ground state, which is convenient, of course, if you want to do a Bqe. So the first experiment was then to calculate the baryon mass. The baryon mass exactly is the gap between the baryon energy and the vacuum energy. So what it means is that we ran 2 experiments. The first one is creates a ground state in the B=1 subsector. So you get the energy. Second one, again, ground state preparation, but this time in the B=0 subsector. And then you subtract the energy, you get the gap, which is your baryon mass. And we did this for n=4. n=4 is 8 qubits because it's 4 lattice sites, but you have 2 colors, right? Which makes 8 qubits. The IBM Casablanca chip has only 7 qubits, but with circuit splitting, we could reduce it to 5 qubits. And I noticed that I run out of time, therefore I don't explain much here, but we were very happy to see that, yeah, the Bqe results matched the ED results pretty closely. For the meson mass, it was more complicated because the meson is the first excited state. Preparing the first excited state is more complicated. In fact, it also requires a modification of the cost function. There are several ways to do that. The one that we picked here is first to search the ground state. And then when searching for the meson state, modify the cost function such that you penalize overlap with the ground state. And yeah, I can say more about this later, but it's a more resource efficient, resource intensive way of Bqe, and it allows you to get excited states. But since it was more resource intensive, we did it only for n equal 2. Since I used 43 minutes already, I have only 2 minutes left. I will jump over this unless you ask me later, that we can also compare how do the mass of the meson and the baryon compare, and how does this change if you increase the lattice height. I found this very exciting. But for now, I will just summarize that, yeah, this was the first study of a non-abelian lattice gauge theory with dynamical matter on a quantum computer. It was a proof of concept demonstration with the aim to pave the way for future simulators, and really in the spirit of hopefully developing more and more capable quantum simulators as we go. This is my last slide, which is an outlook. Yeah, and it's something else entirely. It's just letting you know that we're also looking at completely new possibilities, like completely different things for quantum enhanced computing. Yeah, and as I said, I'm a fan of variational quantum eigensolvers because they allow us to address complex problems. And here in this publication, we looked at the variational quantum eigensolver, but without entangling gates. No entangling gates at all. In fact, only local operations and local measurements. And yeah, it looks very different if you start designing algorithms with that. So that's a new approach for algorithm design. But most importantly, my personal hope is that since there are no entangling gates involved, but only local operations and local measurements, I hope that it will open up a whole new generation for experiments with photons. Yeah, so I talked to someone from Xanadu recently, and they ruled out doing VQEs entirely because they said, entangling gates with photons, forget about it. But with such types of approaches, it might become really interesting. And I have seen what VQE did for qubit-based simulators, and I would love to see a similar development for not qubit-based, but photon-based simulators. But that is very new, and it's also not the topic of today's talk. So I only conclude with saying that we have a lot of unexplored territory ahead of us, and yeah, I'm looking forward to seeing where this journey will take us. Thank you for your time.
Thank you very much, Christine, for showing us these very nice results, and also a very inspiring talk, and very clear as much as is possible in compressing so large amount of work in only 45 minutes. So thank you very much. So I remind the audience that you can write your questions in the chat, and I will read them. So here comes with some of the first questions by Orlando Oliveira. These were already there during the talk, so I think he refers to something at the very beginning, actually. So when you introduce lattice gauge theory formulation, so he asks, suppose that he supposed that the simulations refers to Euclidean formulation, or it works also in Minkowski space.
I'm not even sure I understand this question. So like it's in a Hamiltonian formulation, right?
Yes.
But maybe you can help me to understand.
Well, I think he refers to having, please.
Oh, because when Minkowski space, it makes me think of a Lorentz invariant simulation,
Indeed.
which is what we cannot do. No, we are absolutely not Lorentz invariants. We brutally break time-space symmetry, like as soon as, but simply by going to the Hamiltonian formulation, right? Simply by doing that, like we keep our space as a lattice, and time becomes a parameter which is continuous also. We have discrete space and continuous time, and I think as soon as we go to the Hamiltonian formalism, like Lorentz invariance is out of the window, right? But I don't know whether this actually answers the question.
I think that was, it is exactly the question, the answer that he was looking for. And also a follow-up question related to that, well, to the introduction of a model is, what about truncation and gauge invariance? I think he refers to truncation of a gauge field.
Yes. Oh yeah, that's very important. Yeah. So in principle, if we write down the Hamiltonian, it's a gauge invariant Hamiltonian per se, right? And then the question is, what happens if we truncate the gauge field? Well, formally, we only recover. I mean, I was about to say that in principle, we get the correct symmetry transformation back, but the thing is that we do something to the commutation relations, right? So like we have for our gauge fields, the original commutation relations that we in principle need to do all the transformations, and there's an error in that. And the only thing that we can guarantee, that we recover them in the continuum limit, because that's how we make how we build the truncation. And also we know how the error basically shrinks. Yeah. But of course, on the way there, we do have the error, and like we do not have the correct commutation relations. Yeah, so that's true.
So it's an approximation which is kept under control, I would say, right?
Yeah.
So then we have another question, which is related to, so I just read it. So you mentioned wanted to explore qubits before. What advantages do you expect? Also, do you have a platform in mind, since that they are harder to implement?
Yeah, yes to all of the above. Yeah, so I think it's just so much more resource efficient. So I'm thinking about the gauge fields in particular, right? So the gauge fields, they're defined in this infinite dimensional Hilbert space. For the models that we're looking at, the smallest, the minimal meaningful truncation is three levels. Yeah, so we don't see the physics that we want to see if we have only two. So it's not a qubit. It's at the very least 3. And we even see that for some regimes, we even need 5. Yeah. And then, so what we're currently doing is we use the 3 levels and encode them in qubits. Yeah. But instead, you could use a spin 1 system for the 3 levels. Yeah. And so we looked into this, and it gets more resource efficient in the number of particles. Like we look at it for ions. Yeah. And you need fewer ions, which is a no-brainer. But which is also important, you need way fewer gates. Yeah, the saving in terms of gates, if you use qubits instead of qubits, if you want to have a 3-level gauge field, is also very big. And so for me, there are 2 platforms which are especially interesting. The first one is trapped ions, because in trapped ions, we will see a new generation of experiments soon, which can have interacting spin chains with spin 1. So proof of concept has been done. I mean, back in the times, Crystal Senko was the first author where they implemented an interacting spin 1 spin chain in trapped ions. And now there are several groups who are implementing a new generation of these. So like Crystal Senko, for instance, here at IQC, but also Rainer Blatt in Innsbruck. So these spin chains, they will come for sure. Yeah, and so that's the most promising one from my perspective, but something that we're also investigating, like me personally in my group, and we have a publication coming up on that, is in photons, in microwave photons. Yeah, so you also have a nice big Hilbert space. We have more than 2 levels, and so you go about it very differently than you would do for the ions. Yeah, like it looks formally very differently, but there you can also encode your gauge fields in not qubits, but larger Hilbert space. One of my favorite topics.
Great, thank you. So while we are waiting for further questions from the audience, I have also some curiosity. So, and the first one is, so given that now you have you know, dived into all this work of encoding, do you have any estimate or expectations for, you know, the minimal amount of qubits or that we will need to start to get some real interesting results in the field? You know, like with Shor's algorithm, we need, I mean, typically we say that we will need 1,000 qubits. Do we have any kind of estimate for our field? Yeah, for lattice field.
Yeah, that's one of the key questions. So let me maybe specify what interesting means. So I specified what interesting means for me. Okay, so it might be different for other people. So interesting for me would be that I can simulate a model that cannot be simulated that can be simulated with a quantum. So I outperform a classical computer on a model that is physically interesting. Yeah, so like not an academic model, but so for instance, it could be a 2D gauge theory with finite chemical potential, for instance, which cannot be treated by Markov chain Monte Carlo, for instance, or it could be a time evolution, or it could be a 3D gauge theory with a topological term. So something where there is like a physics interest, but we outperform classical computers. So that's something that I would love to see. And the question is, how many qubits do we need for that? Yeah. And to be completely honest, I don't know. I can only, yeah, I don't know. I would love to know. I would love to know. But like my current guess at the moment is that maybe with 100 qubits we can do it, and I think the limiting factor will be actually the gate depth, right? Because if you give me 100 qubits, I can probably do a toy model. So for instance, with finite chemical potential, I can write it down, and 100 qubits will be enough. Yeah. However, we are not going to run it because errors accumulate and kill us. I mean, even if we do everything that we can think about, circuit splitting and like all the tricks that we have currently, yeah, so gate depth will not be sufficient.
I see. Okay, good. That's a good answer. So it's already gives us an idea of how tough is the challenge that we have had.
Yeah, yeah, but that basically probably translates in the number of qubits, because if we wanted error corrected, then of course it blows up by a factor 10 to the 3 to 10 to the 4. Yeah, so.
Then the last curiosity is related to your last work that you have flashed, which is actually very, very intriguing. And I admit I didn't know that. But I have
only be published on Friday, so.
Okay. But you know, the idea is very, very intriguing, but if you have no entanglement and only single.
Oh, no, we haven't. Sorry, we have a lot of entanglement. It's just that I was not giving you the whole truth. So okay. what it basically is, we marry two approaches. So one is this hybrid optimizer, the Bqe, and the other one is measurement-based quantum computing.
I see. Okay.
Yeah, because all Bqes that are on the market today, they are all based on the circuit model, right? Understandably, but circuit model is not the only one we have. No, you can do quantum computing perfectly well with the measurement-based approach, right? And in the measurement-based approach, we have a highly entangled input state. This is where your entanglement comes in, and then you use it up. I mean, I think you know this very well, right? Where the computation is just a sequence of measurements, yeah? And so on the one hand, you can make a direct translation for Bqe to measurement-based. But on top of that, you can also think of brand new things. Yeah, so we call it, for instance, state variation by edge modification. It's a different way of thinking, and where you can even do things that have no direct analog in the circuit-based model. So in a sense, what we need is an efficient way to make a highly entangled input state, but it can be also probabilistic. But once you have your highly entangled input state, basically your calculation is just measuring. And this is where the entanglement comes from. You need entanglement one way or another.
Indeed. Great. I don't see any other further questions. And so I would say that I thank you very much again for this very nice talk, and all people in the audience for attending this talk. And I would ask for the final slide that announce our next talk on the 7th of July, an experimental oriented talk by Fred Jędrzejewski, which will speak about engineering local U1 symmetry in artificial systems. So thank you again, and goodbye.